recording. Yes. Today's delightful topic. So, your lucky day. There are donuts here. Help yourself. They were warm when I got them. Lucky's at 7:05 this morning. So apparently somebody there shows up really early and makes those donuts, and they're in the case. There's a small box of gluten-free donuts if you have gluten intolerant. And then I will take whatever's left over and torture Margot with them. I don't know, did anyone take 313? So you probably remember Margot. She's difficult to forget. So project 4, how many of you are done with project 4? Like 40%, roughly. How many of you have even started project 4? My favorite are the people who actually don't start the project until the extension. Usually like the day before the extension is due. Those are always the killer ones. Interestingly enough, when I do analysis of that, I find that the plagiarism rate amongst those people is off the charts high. I wonder why. So against my better judgment, I acquiesced and gave another week. And of course, I was commenting on this, then Discord went absolutely silent. So people have obviously decided they don't need a week, so they're going to wait until next Monday at 7 p.m. to finish it. And thus it's a zero-sum game. I would strongly encourage you to finish Project 4 and start looking at Project 5. Project 5 is worth as much as Project 4 and is probably comparable difficulty. And there's no extension on Project 5. That's UBC says has to be done April 13th. Project 5 is released. It has been released for a long time. I don't think last I looked, no one had submitted a Project 5 yet. But I know people are working on it because I know that at least one of the TAs asked me a specific question. But the final has been scheduled for April 20th, 2023 in DMP 310. I don't know why they decided to put us in there, but they did. So I haven't decided on the format yet. I'm working on that. I don't have a prior final that I've used for this class, so I don't have an example. I'm going to steal one from Ivan as soon as I send him an email and ask him for it. So I know they allot 2.5 hours for the final. I don't expect it will take that long to complete it. I mean, it shouldn't have more than 300 or 400 questions. That's how you set limits that people look at and go, oh my God, 300 or 400 questions, I'm not going to survive that. And it's like, well, no, that was an upper bound. And it was just a sloppy upper bound because I didn't really want to think about it yet. I mean, my goal in the final will really be to try and analyze how you apply what you've learned. I don't want it to be a lot of memorization. I want it to be, given a scenario, what tools would you bring to bear here and why? And those are hard because it means you actually have to do some analysis there and you'll be going, but it's just what we've been doing. It's what we keep doing over and over again. Why do we do these things? How could we optimize this? How could we get rid of more network traffic? That's all that we do in like Project 4. Is a lot of it is we take what's a very basic protocol and then we try to optimize things out. So we end up doing things like doing batching, for example. Because when we're building that Martian data center, batching is going to be really important. Let's see. Oh, okay. So people who are doing alternate path, you now have the option of doing a 10-minute presentation on April 13th. And that will be considered as part of your final report. Choose to do that. And I'll ask people to let me know if they want to do that option. There's only five groups doing alternate path projects. Nothing else has changed. I suggested the Dynamo paper before. This time I'm actually putting it on the required list because that's basically what Project 5 is. It's Dynamo, or it's some scaled down version of Dynamo. How do we take a key value store and scale it up and make it robust or resilient? A couple of other interesting papers, and the reason I'm including these is mostly to help you understand why we focus on key value stores. They are used everywhere, all over the place, all of the time. So I picked two completely different key value stores. One which is a high performance event store, and it's specifically built to be very reactive with high write loads, which is a different workload pattern than we typically see with key value stores that are used for things like Dynamo, where they're web caches. And then KV Direct, which is, at least in 2017, and I haven't seen anything that's beaten it thus far, was the fastest key value store that anyone had written. And the way it achieved that speed is through a series of interesting optimizations where they actually said, hey, let's have the network interface card talk directly to memory. And we will set the values using an RDMA interface, remote direct memory access. So what it means is that a process running on a different computer changes the memory on your computer without you going through your CPU. It literally does it from the network interface card. And they were doing something like 150 million operations a second or some insane number. I don't even remember the exact number, but it was extraordinarily high performance. So that gives you a sense of why we talk about key value stores and how very different they can be in actual implementation. If you end up building distributed systems professionally, you will probably be called upon at some point to build something like this. And so it's good just to understand why they're useful. It's a super simple interface to understand, and we can scale it up. We can scale it up, we can scale it out. Both of those things are really important. Anybody have any questions at this point? So I am curious, how many of you actually watched the guest lecture? Almost everyone. Interesting. Maybe you just didn't want to raise your hand because you're tired. Oh, it's too hard. I can't get my hand up. I don't know. How many of you enjoyed it? Great, great. That helps me know whether or not guest lectures are actually a useful break in the monotony of listening to me drone on and on. Anybody have any funny stories? He's got a funny story. There we go. There we go. That's an interesting failure case too. I like that. Today's failure is a little more whimsical. Does anyone in here actually know of there's a social media site called Reddit? Anybody use Reddit? I mean, I'm kind of amazed because Reddit's been around for a long time, and you know, people who have abandoned things like Facebook, and I don't know about you, but I've pretty much given up on Twitter. I mean, I know people who use it for their porn feed, but that's just because they can't use Tumblr. You guys laugh, but I have to tell you that working in the tech business, one of the things I learned is a long time ago is how much adult entertainment drove a lot of the things that we do in tech. It's very interesting. I actually taught one time in a company called Data General, which I don't think exists anymore, and they made rack mount servers. And they actually had a group that had to do support for their customers. And one of the qualifications for joining that group was you had to agree that you were willing to see adult material as part of your job, because people's servers would stop working and they were serving porn. And you'd have to log in and you'd have to look at stuff, and you might inadvertently be exposed to that. Unless you think this is an exception, I actually had a guy in class one time at Microsoft who said that he had a written exemption from legal and corporate affairs requirement, LCA being the lawyers at Microsoft, where they say you can't have porn on, at work. He had a written exemption to that. because he ran the content filtering group. And it turns out it's really hard to build a content filtering group and run it if you can't actually look at content. Yeah, March 14th. That was Tuesday. Reddit went down. I love it. This is right off the website. They didn't actually tell us what happened, but of course, Reddit being Reddit, there's a speculation, which will be in the next slide. So at just after noon. Oh, Reddit is currently offline. Oh, I'm so sorry that happened. What happened? Oh no. We've identified an internal systems issue. We're working to determine a fix. Wow, my leg just went up and hit the desk. Surprised the hell out of me. We've identified a fix which may take some time to implement. In the meantime, ready your bananas or eat them. The Reddit people are kind of odd. This is them hitting the desk a second time, and they just keep hitting it. We've implemented our fix, and we're slowing allow things to ramp back up. Recovery takes time. It took time in Project 3. It takes time in Project 4. Putting things back into sync is actually a hard problem. And one of the things that makes it hard from a real engineering perspective is this stuff doesn't go wrong very often. So you end up having to debug code that only runs rarely and only when things are bad. And getting that to work right is surprisingly challenging. And then they actually don't have it resolved until more than 5 hours later. So of course, the best theory I saw on Reddit of what was causing it was caused by this invasive North American species known as the fiber-seeking backhoe. And I just thought this was absolutely priceless. It is a great graphic. And everybody needs a little humor in the morning. You can read it from the slide. I don't need to tell you what it says, but the takeaway for this is our takeaway from our class. Networks are fragile. Networks fail. Networks can be fixed. And these are the things we have to deal about. When people are sitting there complaining about partition tests, guess what? It's the backhoe hitting the fiber optic cable that just breaks the link between two data centers. I hate when that happens. But then somebody comes out and they fix the broken fiber, or they route the traffic in a different way around the broken fiber while they fix it. And then the network heals. And we have to deal with that. These are the kinds of failures we have to deal with in real-world systems. It might be a backhoe that hits a fiber optic cable, but our reality in our data center is it means that our Paxos implementation or our Raft implementation or our PMMC implementation or ViewStamp replication or whatever you want to call it today, they're all the same thing. They're all our distributed consensus algorithms. We have to handle it. And that's the important takeaway here. This isn't something that we arbitrarily create to torture you with projects 4 and 5. It might feel like that. And I said this at the very beginning. I said, this is a hard class, not because we try to make it hard through obfuscation, but if we give you everything and we tell you all of this stuff and we give you code examples, it's still hard. Because dealing with failure is hard. Today I'm going to talk through the Project 5 sharded key value store. I know that most people haven't finished, well, I can't say most people, a significant number of people haven't finished Project 4. But I wasn't going to stop talking about Project 5 because there's quite a few people who have already started it, and I want to make sure that we walk through it and at least provide you with a basic overview. So the first thing I'm going to do is I'm going to review this concept of consistent hashing. Consistent hashing is explicitly covered in the Amazon Dynamo paper. I actually put a link to it on the slide. That is just the Wikipedia article on consistent hashing, which is actually not bad either, and provides you with a basic description. In essence, what we do is we think of consistent hashing as being a circle. That's our key space, or our mapping onto the key space more specifically. And we divide that up based upon the number of different places we can store keys. That's what we're talking about when we call them shards. You'll notice in that picture, and it's very deliberate, those pieces are not necessarily uniform size. And the reason that we want to allow them to be different size is because we don't necessarily have a uniform distribution of the keys themselves, and we don't necessarily have a uniform distribution of the load or the use of those keys. One of the things we see all of the time, especially in social media platforms which use key value stores underneath them a lot, is that things get hot. We have trending items. And so everyone is trying to load the same exact item. And we can change our sharding dynamically in order to accommodate that kind of load. Now, frankly, if you have a hashing algorithm that isn't giving you good scatter on your input set, you probably didn't choose the right hashing algorithm. That's a completely different issue, but we can still deal with it here. So we divide the circle up into chunks. And then we hash the key we're looking for, and we take that hash and we compute where we think it should be, and then we go to the next shard and we say, where is the previous shard? And that's what allows us to insert things. We don't go to the shard where we think it is, we go to the shard after that. And we say, what's here? And it'll tell you what the boundary of the previous one is, and then you can go back to the previous one. Kind of an interesting model. Now, you could actually optimize this clearly. You could call and say, what does the current shard space look like? You could get a whole table of these things. You don't have to do incremental lookup. You could say, give me the whole table, and then, wow, we could run some sort of caching algorithm on that. Make sure that I know what the current shard space looks like. There's a pretty cool video. I think it's Nick Feemster who taught 6250, which I took. Only networking class I've ever actually taken. And the only thing I actually didn't know about in that class was software-defined networking, which is relatively recent. The rest of it, I lived through it. It's a good discussion of consistent hashing. If you prefer videos of these things rather than like listen to me ramble on or read a Wikipedia article or read it out of the Dynamo paper. The Dynamo paper also talks about consistent hashing. This is a consistently used technique. The way that it's implemented can vary, but the fundamental idea of breaking up your space, your key space, in this sort of flexible way is pretty much used by anybody who tries to distribute their key value stores or other kinds of load balancing like this. It gives us good load balancing. It also gives us dynamic scaling, and those are both important to us. You can actually take things out of it as well as merge existing shards together. So what is sharding? I kind of liked this picture because I thought it was a really simple description, but what I didn't like was that it actually doesn't use consistent hashing. What it uses instead is just a static sharding of the key space. This is the naive or simple way to do this, is to say, well, okay, I've got keys that go from, 0 to 100, and I'll just simply divide it up into 5 chunks, and each chunk has 20 things in its space. Actually, the first one has 21 things in its space, and the last one has 19, but who's counting? That's the problem with zero indexing. Have you studied RAID storage at all? You know what RAID storage does. So there are basically two models. Well, there are several models in RAID storage, but there are two models that are predominantly used. One is where we use a set of disks together to create a replicated image. So like we take 3 disks, one of them we use for parity, the other 2 we use for data. And what that means is that if we lose one of the drives, we can compute what the actual data was. And this is a simple implementation of what is generally known as erasure codes, where we have redundant information that we stripe across. A really simple model in RAID is what's called RAID 1, which is I take 2 drives. This is project 3. I take 2 drives, and they're exact copies of each other. And anytime I do an update, I can do it to both of them, and anytime I read, I can read from either one of them. Very simple model, very straightforward. The problem, of course, is that it has 100% overhead. People will then take a RAID 1 set, and they will take another RAID 1 set, and they will do what's called RAID 0 on it, which is they stripe across it. So they could put like alternating blocks on each one. So now you have a logical disk that consists of block 0s here, block 1s there, block 2s here, block 3s there, so on and so forth. And for all intents and purposes, when we start sharding our key value stores, what we're doing is kind of like RAID 10, the RAID 0 plus RAID 1 combination is called RAID 10, where we mirror and we stripe. But in fact, we're not really just mirroring down below. We're actually running Paxos, so we get the benefits of having multiple copies. Having 2 copies of the data isn't good enough. We're going to have 3 or 4 or 5, probably 3, 5, or 7, 9, because we've already learned that odd numbers are our friend when we do distributed consensus. And then we chunk up our key space, and we distribute the keys across that key space. Really all we're doing. So in project 5, we have Paxos running. Paxos is running underneath key value servers, just like project 4. But now what we do is we put a key value store front end on top of our key value store, and we shard our keys. So what that means is that we have these groups, and each group is a set of key value stores, but we have a thing on top of that, a layer on top of that, that takes those and routes them to the different sets of key value stores. Each of those sets of key value stores is a group. That group is replicated. We replicate it using the Paxos protocol. We shard, we split up our key space, and we distribute it over our set of shards. So we have a whole series of clients. And in this implementation model, what we're really building is what will probably become a library that an application uses, because the application doesn't want to know about our sharding. So we build a library that the application will link against. And this is just a software engineering thing. It's not really a fundamental concept. But from a software engineering perspective, I'm going to build a library that understands I need to go fetch the shard configuration so I know where to route the messages. And you can actually build this so you don't do it that way. So you could actually just send it someplace and it gets forwarded, or you send it someplace and you get a message that redirects you to the correct location. Those are all viable solutions. There's a lot of different ways this could be implemented, but we're going to keep it simple, and we're going to say the client calls and says, hey, what is the current shard configuration? Now, of course, we're going to have to deal with the case where the shard configuration changes. So how do we keep that cached state now? I ask you what the config is. I don't want to ask for the config every single time. The problem with asking for the config every single time is that it's going to take too much effort. It's going to be too much overhead. So I'm going to take that config, and I either need to be notified when it's changed, or I need to have a mechanism where if I send a request to the wrong shard server because there's been a reconfig, I get a notification that says, actually, you're not using the right config. Gosh, this kind of sounds like a view or a ballot. Same thing. So we're told So these kind of act like proposers again, don't they? They say, "Hi, I want to do this thing on this shard," and it comes back and it says, "Well, actually, you're using the old view. You're using the old shard configuration. Same concept, slightly different term." I get the configuration. I use the configuration to route my request to the correct shard group. Question. What is the difference between the Paxos client and the shard store client? Well, the shard store client is actually not running Paxos. It really is just simply saying, where should I send this request to? Any replication that's going on is happening in the back end, in the servers, not in the client. Okay. I'm sorry? Mm-hmm. Right. The key value stores, the actual sharded key value store interface is the Paxos client that's running, it's using the shard masters, right? So you have two different layers at which you're doing consensus now. You're doing it within the group, and then you're doing it across all of the different shards. Because it's but we're doing it for different purposes. So the one that sits on top is the reconfiguration protocol. We're actually, do you remember when we talked about Paxos? Lamport does actually lay out how you can do reconfiguration in the Paxos protocol itself. We are, in essence, building a separate layer to do reconfiguration. That's really what we do in the shard servers. The only time we actually have to go and agree on anything is when we're going to change the sharding, which is the configuration of the sharded database. Yes, and that's the one that's managing the actual. Yeah, so it's the one that's actually managing the sharding protocol, the configuration of the shards. And then we would also have the same protocol, or we'd have a Paxos protocol that's running inside of each group to give us the replication. Although I don't know why we'd implement that in a test framework, because it's not that important. We'd still need it. So we have a shard master, and in this case, the shard master is not something that you have to implement because this is, the client that is talking to this is not what you have to implement because it is part of the test framework itself. So it's going to be triggering the reconfiguration events. It's going to be doing the things that you have to actually agree upon in your group of shard servers. So that's the client, and this would be the Paxos implementation itself. Let's see. So the shard master is just an application. And I know I've mentioned this before. We have a composability in our distributed systems here and using these distributed algorithms. So we can compose our systems. We can have a layer here that's running Paxos, and then we can put a layer on top of it that's running Paxos. And this is what we're doing. And now what we're doing is we have Paxos agreeing for what goes on inside of a single shard group for our replicated copies. And then on top of that, we have another Paxos instance that now agrees on what the configuration is of our sharding. And it's turtles all the way down. And if you don't know that reference, it's Terry Pratchett. And I think it's several other cases, but I know the Terry Pratchett one where somebody says, in his world, the Earth sits on a turtle, and then somebody says, well, what does the turtle sit on? Another turtle. And then it's just turtles all the way down. And this is what we do. We go to work, we build systems, we put layers in them, and I've made this analogy before. It's like, anybody who likes cake knows that a 2-layer cake is better than a 1-layer cake. And a 3-layer cake's even better than that. And that's exactly what we're building. We're building an n-layer cake here, and it really is only 2. But in the real world, people then take key value stores and build distributed databases on top of them. Mongo database, MongoDB, is built on top of a key value store. And then they actually have a sharding protocol. Go figure. And so they do sharding on top of Wired Tiger, which I know those of you, several of you said you'd taken 313 with Margot. Margot's husband built the key value store that Mongo uses, called Wired Tiger. It's an open source project, and he spent a lot of years working on that. And it's super high performance, and that's why Mongo ended up buying Wired Tiger and integrating it into Mongo. But then they still need to have distributed replication. And so we solve the problem down at one level, and then in the next level, we solve a different problem. And we can keep doing that, because now we have this nice Mongo database, but I want it to also work with my SQL database. So now I build another layer on top of that that builds distributed transactions. Well, once you start building distributed transactions, you're back into Paxos implementation again. But why would you do that? Well, because you need consistency at a higher level than you get from the key value interface. Because now you want SQL level transactional consistency. And that's the whole point in the database community of SQL having transactions, is so you can interoperate with multiple databases and get consistent outcomes. Well, let's say I take the money out of the deposits database and I take the money out of the ATM's database and I dispense the cash to you. And those distributed database operations have to actually in turn be coordinated, because if the money jams in the machine, you don't want your account debited. But it's still kind of messy, but it's still something that we have to build another layer on top of. So that's the whole idea behind Project 5 is, okay, we spent this time torturing ourselves with Project 4, getting our Paxos implementation to work, and it was so much fun, we're going to do it again at the next layer. So maybe eating the multi-layer cake is fun, but making that multi-layer cake is a lot of work. So P4 Paxos is providing us with the fault tolerance of the individual shard application. See, these aren't really tied to each other. No, they're not really tied. They're not tied to each other. The moment I shard my key space, each of those shards is independent of the other shard, exactly the same way as if I had two completely disjoint key value stores. There's no dependence on them. The moment that I create a dependence, because I've now created this higher level key value interface on top of a lower level key value interface, I have to do the same exact thing. That's why this is layering. Okay, so your Paxos client is the one that actually does the reconfiguration here. It does the moving and joining of the individual shards. So I have to move keys, because this is where that relationship now, when I said they're just separate key value stores, you don't have to worry about it, except when you reconfigure. When you start reconfiguring, now you have to move stuff between these shards. Oh, I added another server group, and so I now need to take some stuff from other shards and move it here because my hashing has changed. Okay, well, the key value stores themselves don't know anything about the other key value stores, so they don't provide this functionality. So we have to build this functionality again. And it just happens to use the same tool set because it's the same problem. We need to do this in a way that maintains consistency, even though what we're doing is moving the data around. Now, I've said this several times. I will say it again. And I heard that. That was one of the things I really liked from Tuesday's talk. I heard that. Moving data around on the network is really expensive. And it's something we try to avoid as much as possible. And what I liked about the problem that was laid out on Tuesday is maybe we can get away with moving something that's kind of sort of close to what we need. And it's good enough. And that's a real world kind of solution. In our databases, we don't get to do that real world kind of solution, but we still have the same problem, which is that moving data from one server to another server is expensive. So we're going to try and minimize this as much as we possibly can. And that's why you get those kind of hand-wavy comments in the README file that say, well, you don't want to move too much data, blah, blah, blah. Because that data movement is really expensive. And while you're moving that data, you're going to end up having an old copy here and a new copy there. And you're still going to be getting queries against the database. So you still have to actually maintain consistency, because the higher level interface that the applications are using to talk to the shard to say, hey, I want the value of this key, or hey, I want to modify the value of this key, they're going to keep going. You don't get the luxury of saying, hey, let's take the machine down for 5 hours and do a shard reconfiguration, because that's where we're going to work really well. It doesn't work that way anymore. People expect this is going to be done live, and it's going to happen in the background. I can tell you from personal experience, it makes everything slower while you are reconfiguring. A significant amount of actual engineering work goes into trying to minimize that impact as much as possible. People complained in Project 4 about having to do batching. It's not something we just made up to torture you. It's something you really have to do in order to make this a viable solution. You picked the sunny spot. Yeah, well, and this is Vancouver. It's not supposed to be sunny in March. So somebody's breaking rules here. Either you for bringing the sunshine, or picking the sunniest spot to sit in, or the deities responsible for the weather. All right, so the shard store client gets the shard configuration from the servers using a Paxos request. Let's see. Shard store request is a change, and then a reply is the response to the change request. Gosh, it's just different labels on propose and accept. Okay. In the shard store server, which is much more interesting, let's see. We have the shard master group. We get a Paxos request. The clients are doing same thing, shard store request, shard store reply. That's from before. But now we have to deal with the other server groups where we're moving things around. And we have to have a transactional layer on top of that to ensure that we are moving them in a transactionally consistent fashion. One of the requirements in 2PC is isolation. For the duration of the time that we are moving shards, no one can know we are doing that. They can't be exposed to inconsistent states. That's the C, consistency. A, the atomicity. So, when you think of atoms, you think of very small things, and yet what I've just described is not small. Right? Moving large chunks of database from one server to another server is hard enough, but now we're moving it from one group of servers to another group of servers. There's a lot of activity going on inside of the individual groups. I think you can see why this is a hard problem. What do you do when you reconfigure? Well, we'll start with the initialization problem, which is we have this circle that represents our hash space, and we get our first group that comes up. Well, everything has to go on that first server. And then when another server comes up and we decide that we're going to shard our space up, now we're going to have to get a new configuration. We have to send the shards that no longer belong in this shard group to the other shard group where they do belong, or shard groups, because inserting a server doesn't necessarily just move everything to one other server. It could potentially be moving it to different server groups. Then, let's see. Of course, once the new group gets the new data, they have to then in turn distribute that internally using the standard Paxos protocol, because we have a replicated key value store. And it really is just the same thing at two levels. The problem, of course, is that you start thinking about that and you're going, wow, this is a lot of permutation going on here. And I personally look at it and I think, wow, all the things that could possibly go wrong. How am I going to deal with them? How am I going to even think about them? Remember that brief introduction to formal verification? This is part of the motivation for it. You can actually do formal verification on the individual pieces and then model another system where those individual pieces now become the things that look atomic to you, and you build your protocol on top of those, and you can formally verify that. You don't end up formally verifying the whole system end to end. You do it in pieces. You can keep it simpler that way and try to reason about it. Does it mean that it's going to work when you're done? No, it doesn't. The problem, of course, is that it means that there may be interdependencies you didn't fully appreciate. But if you try to build a formal definition of a multi-layered Paxos system like this one and then prove it, it will never happen. The state space will blow up. That's why I said, even just wrapping your head around this as you start thinking about all the things that can go wrong, that's our state space explosion problem. All right, so we replicate the shards. Once that's done, then we can update the shard info. Okay, now I've got that new data from the old keys from the old servers into the new servers, and now I can update my configuration to point to where you're supposed to go. And then you tell everybody I'm done. So this is, in essence, command execution. Remember, you get a command, you execute it, and in Project 4, it wasn't that hard. Those commands don't take very long. These commands do. Suddenly, these are commands that could potentially take minutes or hours to complete. And that will make things from a real-world implementation perspective a lot harder. Did anybody do garbage collection? So garbage collection is the realization that at some point everybody has applied all of the changes described in the log up to a certain point, and therefore I don't need to store them anymore. One of the things that makes your life easier is if you can keep your logs small. Partially because the longer or larger the log is, the longer it takes for you to recover it. In theory, you can actually take a database, clean, empty database, and have a log that goes on and on and on and on and never gets truncated, never gets applied to the database. And people do build these kinds of logs, believe it or not. The problem with that is, if the system then crashes and comes back up, now you have this big-ass log you have to actually process. And that takes a long time, and that means your recovery time goes up. The reason we try to keep the log small is because it keeps our restart time down. Nobody wants to wait 5 hours. I mean, literally the reason that I built a journal file system, which is nothing more than a database plus a log, and it's exactly the same problem. The reason I did that was because people didn't want to wait 12 hours for FSCK to run on their hard drives. And that was the way it used to happen, is that, you reboot the computer, or the computer would crash. And literally there was this background process that would come up. Well, sorry, it was a foreground process because you couldn't actually finish booting until you checked the disk for consistency. It would actually run and examine everything on the disk in its database to make sure that it was all in a consistent state. The benefit of using a log was we could keep the log fairly small. The downside to that log was that we had to keep it small. So we had to limit how much activity could happen when the log got too big, because the log was just a finite chunk of space. So the way we did cleaning was we made sure that we updated the database, which is exactly the same thing you did in Project 4, right? Once everybody's applied those changes out of the log, then you don't need that section of the log anymore and you can truncate it. Same exact thing here. But this is long running. And that actually makes the problem much harder because your logs are going to be much larger and the recovery time is going to be much more difficult, and you're not going to be able to garbage collect it very aggressively because you still have moves of shards, of keys to new shards that haven't completed yet. So it's harder to reason about that. It's harder to think about that. You could have a very large log here potentially. So I have a configuration number. We propose a new configuration. What does this sound like? Does it not sound like Paxos? I mean, you could, instead of calling it a configuration number, you could call it a ballot number. It's exactly the same concept. And in view stamped replication, it was the view number. Again, exactly the same concept. So now we're just calling it a configuration number. We have to change the labels to make it more confusing. But it's the same thing. We want to agree to move the system from the current configuration to a new configuration. The complication here is we have an awful lot of state that we have to actually apply before we can agree on that new configuration. Because we've got to move all of that data. We don't have to clean up the old data. We can actually leave the old data in place and clean it up after we've agreed to the new configuration. And that's fine. That's an optimization. It's a very reasonable optimization. Kind of like garbage collection in your log. So I'm trying to move to a new configuration. It's got a new number. That number is higher than the old number. Same exact process. And what we're going to have to agree as part of that process is how are we going to move the data? Because the client doesn't actually care where the data is. The client cares what the configuration is. They care where do I go get the data from or where do I put my updates to that data. But they don't care what the configuration is. That's a detail that the client doesn't really care about. They just want to know, where do I send this message? So in our reconfiguration, like I said, we have to move data. And in this example, we decided we're going to move shards 4 and 5 and from group 1 and 10 from group 2, and those are going to go into group 3. And so that becomes our proposed value for the new configuration. Once we've moved 4 and 5, we tell this server, okay, I've got it now. And this server can now mark those as dead. It doesn't have to actually do anything with the space. It doesn't have to reclaim them. It just has to make sure that it no longer services those shards. Now, it's not too hard to sit there and say, well, maybe we could make some use of those shards before things get too bad. But that's an optimization. And then when we get the other one moved, we do the same thing. And now we have acknowledged that. And in essence, we've done all of the work required for us to move to the new configuration. All this has to be done transactionally. The client selects one group as the coordinator. Oh, gee, okay, so we have a different election protocol. Our leader is now chosen by the client. We didn't do it that way in Project 4. But this could be more like what we see in view stamp replication, which is we just use the IP address to figure out who the leader is. In this case, we just use, in our Project 3, we actually used a view server to choose who the leader was. So this is kind of like that, where something other than the system itself chooses the leader. When we get into Paxos and Raft and PMMC, then we have a leader election. So we elect from within ourselves. We don't have some external force that appoints it. It ends up being exactly the same from our perspective. Once we just need to choose a leader. Once we have a leader, that leader becomes the coordinator. Now we're back into traditional transactional semantics. In order to ensure correct behavior in our transactional system, we use shard level locking. So we lock the individual shards. So while we are moving them, no one can see what we're doing under the covers. The downside of this is it means that anybody who's accessing those shards while they are locked will have to block and wait. And this is one of those places where you might actually think, well, I bet I could optimize that. And you're absolutely right. And it'd be a great question for the final. I'm glad you suggested it. How would you do that? So now the coordinator sends a prepare message, a P1A message, to use the PMMC terminology, as opposed to the 2PC, which is prepare. And then we send a P1B message, which we're now going to call a ready instead of an accept. It's like, why do we keep changing the terminology? I guess the downside to that is it means it's harder to realize these are the same concepts. But the upside is it means that you actually ultimately have to realize it is the same concept. And so you focus on understanding the concept rather than the specific term. And the best part about this is when you build your own distributed system, I would recommend that you choose names that have nothing to do with any of these words so that anyone else who looks at that code will have no idea what's going on, and thus you will be unfireable. It's called job security. I'm joking. Part. Well, not the job security part, but don't invent your own terminology if you can if you can avoid it. Now, we are back to a 2PC protocol, so in this case, we can actually say something went wrong. I can't do this. So we have a 2PC protocol. It's not pure Paxos now, right? Somebody can refuse. I'm not willing to vote. In 2PC, everyone has to vote. And in the model we have here, you have to do it that way because there's only one copy of the data and it's in that particular shard group. And if that shard group says something went wrong, the data didn't get moved to the new shard group, you have to back out. You will need some sort of way of detecting duplicate phase one prepare messages because, of course, it's taking a long time. And I'm going to keep saying, are you ready? 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 How about now? How about now? Huh? Are you ready yet? It's like trying to get your friend to go to dinner and you've been ready for an hour and they're sitting there, I don't know, reading Reddit. I'm almost ready. In the commit case, let's see, so what do we have here? Our current configuration is 1. We do a get on 3 different keys 1, 3, and 5, which happen to be in different shard groups. And we have to have a lock. Right? We're using a lock to make sure that things don't change while we're doing this. If we don't have a lock, then the state of the system underneath us could change. This is why we're using a locking mechanism. Right, so when I accept it, I'm locking. I'm also holding a lock because otherwise I don't have any way of guaranteeing that the system won't change. And these are really independent systems. So this is just database locking. And hey, group 3, why haven't you committed to my change here, my get operation? And it says, oh, sorry, here, I'm ready. And so now we have locked the values of keys 1, 3, and 5. There you go. And now you tell everybody that the world is good, good to go. Locking 3 keys on a get doesn't actually require any mutation of the underlying databases. The only reason you do that is because you want to get a consistent snapshot of what those values are at a single instant in time. You remember Spanner? In Spanner, you had a period of time you had to wait because you had synchronous clocks. It's this kind of system is exactly where you'd want to do that. You'd want to say, okay, I have to wait at least so long because I know what my clocks are, so I can give consistent results. I was trying to think of how do I get out of using strong locking here, and that's kind of what the Google Spanner people were trying to do. You could ask for it, and if everybody answers you within that window, then you know you've got a consistent answer. And if somebody takes too long, you got to do it again. And you do it until you get a consistent set of answers, i.e. within the time window that you're allowed in Google Spanner, which was like 10 milliseconds or 30 milliseconds or something. And that's kind of a cheesy way of doing locking. But they only needed to give a consistent response. Once we've committed the transaction, then we're done. What happens if somebody wants to abort for whatever reason? Okay, so I do a get on the key. Group 2 says okay. But here the problem is that group 3 is on configuration 2, not configuration 1. So it gets that request. I'm sorry, your request, which specified config 1, is stale or old. I'm not going to answer you. So I'm going to abort that transaction. So what we're doing is we're building a distributed transaction processing here. And the purpose of the config is the same thing that we did in ViewStamp replication, where when we changed the view number, it was because something changed in the configuration of the system, and I don't want to do, I can't mix operations across config views. There. Now I create a new term, didn't I? Config views instead of config or views. Well, okay, if somebody votes against the transaction in 2PC, nobody does it. So in this case, I unlock. And I say, okay, I accept that we aborted that transaction. And so finally, this is a nice little slide that talks about what the reference Paxos implementation does. So you get a Paxos request. Is it a read-only request? If it's a read-only request, then generally you can just simply execute it. Remember, though, that you, of course, have to make sure that your read-only requests are synchronized against your log. That extreme example I gave earlier of the database where I've never put anything in the database, I've only put it in the log, is exactly the example of why you can't read around your log. There are updates to the database in the log, and I can go to the log and I can read them out of it. And people really do that. This isn't something I'm just making up. It actually is a real technique where you have some sort of an index table that says, here's where the latest value is in the log. You don't generally see this for in-memory stores, but you definitely see it for mixed storage systems. So for an instance, these key value stores can get huge. You might actually have hard drives, real physical rotating platters of iron oxide inside of a hermetically sealed container. Just saw Newegg this morning sent me an ad for 18 terabyte Seagate drives and saving $365 off, which probably means they're about half price, because last time I looked, they were like $700 or $800. And you're like going, hard drives? Don't worry, by the time you're teaching this class, you'll have people looking at it going, what was a hard drive? Kind of like when you show people the save icon. I mean, you smile and laugh about that one, but it is funny to look at that and to realize that the save icon is a floppy disk, and that floppy disk isn't floppy. It's a rigid piece of plastic with a floppy piece of iron oxide inside of it. And then I used the War Games clip on Discord, which is great because we were talking about acoustic coupler modems, and I use this War Games clip. And the best part is I'm looking at this clip and going, oh my gosh, he used an 8-inch floppy drive disk. Wow, it's so 1980s. Most people don't even have floppy disks anymore. I remember when I threw the last of my 3.5-inch floppy disks out, the rigid ones that look like the save icon, and that was like 20 plus years ago. There was nothing better than installing your MS-DOS operating system from the 3 floppy disks that you got to install it. First time I installed Windows NT in 1993, it came on 19 floppies. You had to sit there and put them in one after the other. So, these technologies come and go, but people still actually use hard drives. They actually use them for data. The problem with hard drives is they're slow. So what we do is we put a hard drive and then we stick an SSD in front of it. Sometimes we combine them in the same package. A lot of hard drives actually have flash caches on top of them. And then we put DRAM in front of that. And there are whole techniques, and I told you there's lots of examples of key value stores, and they put these structures called log structured merge trees, which basically say at each level I keep a mini database, and then I migrate from that mini database to the level below me when things go cold, when I don't really need them anymore. Because there's sort of this inverse rule around how much something costs. So the cheaper the storage is, the bigger it ends up being, because usually the higher the density, the slower it is and the cheaper it becomes. And the smaller, really expensive memories are at the top of that hierarchy. And so we end up trickling down. So even in a single system, we can end up seeing the same exact kind of logic. So that's why I said, don't read around your log. Because you could actually have multiple levels of logging. When you look at a log structured merge tree, it normally has 3 or 4 or 5 levels of storage to it. And when you work for Amazon, you work for Microsoft, you work for Google, Google actually doesn't have a cold tier. They have a cool tier of storage, but they don't have a cold tier of storage. But Amazon and Microsoft both have cold tiers of storage. When I was working at Microsoft, they had a project. This was the project they originally said I was going to work on, and I ended up not working on it. Which was called Project Silica, where they actually record data in glass. And you only get to write it once. Super, 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 super cheap. Highly durable. Pretty cool. You only record it once. You don't really want to record it while it's still changing. You only want to write it once you don't think it's ever going to change again. Okay, well, that's fine, but what happens to the data that is changing? Well, you put a layer on top of that, and you put a layer on top of that, and you put a layer on top of that, and Microsoft has an entire storage stack dedicated just to exactly this problem. You have SSDs, you have non-volatile memories in front of that, which is like DRAM with a battery, or Intel had a non-volatile memory that I was working with several years ago that they discontinued, but it was like DRAM, except you turn the power off, you turn it back on, it's still there. And so the point here is that these layered logs like this are very common. And you can't just go to the bottom layer and pull the value out. You can't go to the middle layer and pull the value out because the value might not be there. So you end up going to each level. And so now when we think about that log, I think of a log as being this long linear thing, right? But I can go to that long linear thing and read the current value. And if it's not there, then I can go and read it out of the database. And that's the whole point, is that once I have that command that says, get me this value, I need to get it from the right place. But I don't have to create a log entry for it. In PMMC, they talked a little bit about this. Section 4.5, I had to point lots of people at it. In Section 4.5, it says you have to serialize your gets against things that are in your in-transit log. They said, but you don't need to put an entry in your log. You could, but you don't need to, because it's sort of wasted space. So you just kind of piggyback and say, you can satisfy this get when all these outstanding proposals have been resolved. But you probably only want to do that if any of those outstanding proposals affected the value you were trying to get. Otherwise, just give them back the damn answer. So once you get the get, you have the application, you get the get, you just do it. Here, send it, go back, done. So that's a very common case where we're coming in through the read-only path, we have the application, we execute it, we send the response, we're done. If we don't, then we could just drop it. We're done. And then the client will ask again. So let's see, what happens if it's not read-only? Well, this is the interesting case, right? Because, and then we say, okay, is this latest completed sequence number is greater than the message sequence number? And if it is, then we're done. and we're going to send back a response. We're going to say, sorry, this is old. Do we have, and this is not reading around our log, active log contains the value, and if it does, then since this is a write, this is a duplicate, we're done because we've already done Paxos request n. If it's not, then we check to make sure that it's not outdated, and if it's not outdated, then we actually add it to the log and propose it. So actually, I'm sorry, we add it to our pending list of requests. Can't add it to the log because it hasn't been accepted yet. And once we've had it accepted, we add it to our log and we tell the caller what actually happened. What was the outcome of my put? So if you do a put, you do a put, you do a put, we don't know the order in which those puts are going to occur because if you guys don't synchronize against each other, I'm not going to synchronize you. I don't have to fix. If your code is broken that way, I don't have to fix you. It's a great thing to remember when you're writing actual distributed systems like this. If people above you just send you requests, you're not responsible for fixing their broken ordering. You're just responsible for providing the guarantees of your interface. And the guarantee of your interface is that you're going to provide them with a consistent view. So that's the reason we run Paxos on these parallel commands is we're deciding not to make them parallel. We're going to make them linear. And the best part is once we've defined that order, that's the order they have to live with. But for all it's difficult, we're not solving all of their problems. We're not solving any of their problems other than giving them an interface to a database with a fixed guarantee, a fixed service. I'm sure there will be tons of questions on this as people start looking at Project 5. But Project 5 is not the same as Project 4. It builds on top of Project 4. If you actually have your own working Paxos solution, you can use that in Project 5. If you do not have an active working Paxos solution, you can use the reference solution. The reference solution that is provided in Project 5 has a limitation that it's only a single server Paxos implementation. And as a result, there's a small percentage, about 10% of the tests that will not pass locally. The implementation that's actually stored in the grader is a multi-server Paxos implementation. So I'm trying to, I actually have to take the reference implementation, put it in with the reference Paxos, run it and see which tests, because I don't have a list of the tests that don't work. Somebody asked that, and I'm like, no, I don't have that. So, but the answer I got back from talking to people who spend a lot of time with this is, well, yeah, about 10% of them. Where people spending a lot of time would be Ada Gavrilovska, who's the instructor for class at Georgia Tech. Project 5 is fun. It'll be stressful, probably almost as stressful as Project 4 was. But at the same time, I really wouldn't sweat it. I will tell you that it is not uncommon for people not to get 100% on Project 5. I wouldn't, again, I think the people in this class might be a little more chill, but certainly the people in Discord are kind of panicky, especially the 3 hours before the project is due. Well, all right, it's 5 hours, and then I extended it, and then they immediately decided to go party, I guess. Do your best. That's really all you do, expect to do. This is still worth twice what the final is worth. I think that's right. Or is it about, no, maybe it's worth as much as the final is worth. All right, so it's worth more than the final. It's not twice, but it's worth a decent amount. And don't forget your reports, because your reports are very important. I will probably, next time I do this, increase the weight on the report, because I really want the understanding. I don't really care about your code. You're not going to care about your code. That would be my final piece of advice to you today, is that because for some reason I have a lot of people who are experiencing death in their families right now. which is a little depressing. I had a friend yesterday who said his mother, who had cancer and it was treated, has returned, and it's in her spine and on her liver, which is consistent with a prognosis of less than 11 months, according to the literature. Yeah. So, and that's after somebody else's father just dropped over dead last week, and she's off on the island dealing with that. You will not remember the grade that you get in this class 6 months from now, let alone 50 years from now. It doesn't matter. What I want you to do is I want you to understand the material, and hopefully, when the time comes for you to actually have to start implementing distributed consensus algorithms, you'll go, damn, that old fat dude was right. Take care of yourself. That's more important. That's why I brought donuts, because these say nothing but I'm taking care of myself. And that's it. On Thursday, I will go back on. So the things that we'll be talking about more after this are more, what do we do with these distributed consensus algorithms now that we have them? So I think the next one is Edge and IoT, which I thought would be really cool because that's a nice use for distributed systems, because pretty much everything we do revolves around, this. I mean, anybody have a smartphone? Yeah, as he pulls out his Nokia flip phone. Awesome. Well, thanks very much for coming. Grab something to eat, and I'll see you on Thursday, hopefully. And don't forget to enjoy the sunshine. Today's Thursday, Tuesday.